Welcome to The Dish, where we invite entrepreneurs to share their insights into the next generation of biotech companies. I'm Johannes and Phil, founder and chairman at Lab Central and CEO of Biolabs. After more than a decade of working with entrepreneurs and supporting more than 1,200 startups, I'm here to bring you stories from our ecosystem. Are you ready to dish?
Live from Lab Central lobby at 700 Main Street in front of a live studio audience, please welcome your host of The Dish, Johannes Freuhoff, and his special guest, Phil Sharp.
Welcome, everyone. Welcome to The Dish, and a special welcome today to our guest, Dr. Philip Sharp, MIT Institute professor and Nobel Prize winner for his 1977 discovery of RNA splicing, which of course shapes the modern biotech industry and era. Philip later went on to co-found important biotech companies like Biogen and Alnylam. And so that's what we're here to talk about today. Philip, thank you so much for joining us here today.
Thank you. It's a pleasure.
And we typically start our dish interviews by asking our guests to bring an orange object. Today, we bring you an orange gift. And so Phil, as you will see if you watch his documentaries from Kentucky, so we found an orange object from Kentucky, bourbon, Colonel Taylor bourbon, and we understand that Colonel Taylor was an innovator in his own time, so we found that fitting.
Thank you very much. I love Kentucky bourbon.
Phil, let's get started with talking about your most famous discovery, the splicing of RNA. We have many scientists. Who is a scientist in the crowd? Who has made a similarly important discovery? All right, so please share with us how that feels. How that feels when you see that for the first time, when you understand that. Take us back to that moment.
Well, it's hard to really communicate absolute thrill. But in the lab, we had been working on this issue of how genes were expressed for 2 years at different levels. And ultimately, we came to the conclusion that there had to be an unusual pattern, and we did an experiment in which we saw these 3 loops. And the loops told us that the sequences in the RNA that's the message is being spliced together, and the intervening sequence are being removed. And when I saw it in the electron microscope, I was stunned. We had to collect a lot of data to make sure that it was reproducible and the structures we were seeing were coherent. And then it was, what do you name it?
Oh, what do you call this?
What do you name it? I mean, it's not been seen before. There's no one else. And so we incubated RNA splicing as the name. And then the next question is, you and I and 2 other people understand this, but how are you going to communicate it? How you're going to get it in front of people. And there we reached out to my colleague Dave Baltimore at MIT, who's a member of the National Academy. And I brought him in and we explained what we were doing and asked him to communicate a paper. It was absolutely thrilling, and then the big questions of how to make it meaningful appeared. and the world rolled on. But, you know, you go home and you talk to people, but they don't know what RNA splicing.
How long is the process of a discovery? You knew you were searching for something.
I knew it was for almost 6 months. I knew I was searching for something.
Yeah.
That was unusual. I didn't know the answer, but I knew it was unusual. And then there was a moment in which it became clear. And that was a eureka moment. As the film documentary shows, I was shouting obscenities. I was. There were 3 loops. I mean, what do you see? It says you got 3 loops, the RNA is being spliced together. And I knew that's the way cellular genes happen.
What gene you were looking at?
I was looking at an adenovirus gene.
Yeah.
But there was 20 years of literature that basically said long RNA, short RNA. And no one was really paying attention to it. But then I knew what that meant. That meant essentially every gene was being expressed this way with the splicing. So it was fabulous.
Yeah. And now, of course, that allows us to have all the human proteins encoded by a small number of sequences, relatively smaller number of sequences.
Yeah. It's a secret of how we, with 20,000 genes, have our complexity, whereas a small worm that lives in that soil out there has 19,000. All right? But we have a much more elaborate splicing system, and it's particularly elaborate in our brains. So it's a source of complexity with a limited amount of information. And that apparently, at some stage in evolution, was absolutely critical for forming multicellular organisms and doing all the wonderful things that humans do.
It's an economic way of using limited genetic information.
Limited genetic information.
And of course, it has immediate disease implication because there are many diseases that are caused by splicing aberration or that can be addressed by fixing them.
Yes, more than we know about now. And, you know, there's indications that we're going to be able to drug splicing.
Yeah.
And that will give us a whole nother tool for how to modulate genes and treat disease.
Yeah. So talking about treating disease, I was particularly happy to have you accept our invitation for this interview because you're more than just a basic scientist. You also are a pillar of the biotech industry. At Lab Central now, we do what you did with your peers in the 70s, which is found your first biotech company. Take us back to those years of creating Biogen.
Well, the creation of biotech came out of the academic labs. And you recall in 1975, Cambridge itself was up in turmoil about whether we could do recombinant DNA here in Cambridge. The same year I did the discovery of RNA splicing, I get a call from Ray Schaefer, who was an MIT alum, to go and consult on an investment in a biotech company. And I didn't know Ray Schaefer. And I actually, at that stage, knew nothing about biotech. And I flew out to San Francisco. And in walk Herb Boyer and Bob Swanson, the founders of Genentech. And they showed me a diagram, I probably have it in my files, of the synthesis of the first insulin gene, synthetic insulin, and growth hormone. And they said, this is Genentech, and Ray Schaefer had the option of being the first external investor in a company. And Inco took the option, bought 13% of Genentech. And then there was a conversation that started between Ray Schaefer, myself, Wally Gilbert here, and Kevin Landry at TA Associates, that we should invite a number of European scientists and Wally Gilbert and myself to a conference in Geneva and talk about what recombinant DNA meant, but start a company of encompassing all the East Coast and Europe in one biotech company. That was the strategy. we held the conference. Our European colleagues were much more hesitant to get involved than we were. But we ultimately, in the second meeting in Paris, you'll notice Geneva and Paris and some very nice dinners in all of this. The second meeting in Paris, we decided to go forward and form the company. And it was like sitting there saying, I should tell you something. I was trained as a chemist at the University of Illinois. And 3 out of every 4 graduate students in that very good department were going into the chemical industry. That was their objective, had great careers. And here we had synthetic biology. We could make things. And it was the parallel of chemistry. Could you take this ability to make things and make things useful? And Biogen was founded on 3 pillars. They were going to do biomedical science, synthetic chemistry, making intermediates, and energy. Ultimately became a biotech pharmaceutical company. But it was like being able to found organic chemistry again. And that struck me as, really, that's going to be cool. That's really going to be fun. And let's see if we can make it happen. And we did.
Did you know what you were signing up for?
No. Not even close. Not even close. But it soon became clear you had to raise a lot of money, and you had to engage a lot of people, and you had to create a very good business plan and attract leadership. The one thing I've learned you need to know is if you're going to start a company and you have great science or great management, CEO, take the great CEO. Because if you got the right leader, you can create the science, you can change the science. But it's very difficult to change the CEO. So we made every mistake in the world, every possible mistake. But by being a first actor and getting support, we were able to work through those. Company was established in '78. The first approved product Schering-Plough owned was in '86. It was alpha interferon for a hairy cell. And that's 8 years from founding the company. The gene was discovered in '79 by Charles Weissman. So it was 7 years from the gene, and they got approval. But we were losing money like you couldn't imagine at that stage. We had gone public at 23. We were trading at 4. Talk about sweat. When we were very public at that point. And we recruited Jim Vinson to come in and take over CEO. He was an entrepreneur, a very experienced one. And then we got Avonex, beta cell interferon, working for multiple sclerosis, and off went the sales. And it's a wonderful day when you're cash positive, folks. It's a wonderful day.
Liberating.
It is liberating.
Take us back to those days of the public discussion in the birth years of biotechnology. People were very scared of this unleashing of the genes, and Frankenstein is going to rise and eat us all or something, right? Like this public discussion that ultimately led, in my understanding, to what Cambridge is today. Take us back to those years.
So 75 was the moratorium. It came out of the concern that people were going to make recombinant genes that, if distributed through a bacteria, would create disease in man. And putting tumor genes into bacteria, putting human proteins into bacteria. So that became a concern at an academic debate. Meeting in New Hampshire, there was a letter written to the National Academy saying, we think there should be a moratorium for a year. to get guidelines in place for doing this research to reassure the public that we are considering their benefit as well as our interest in doing this. So we had a moratorium. NIH issued guidelines. The Asilomar Conference drafted some recommendations. NIH perfected those, publicly disclosed them, reissued them. We began to think about doing those experiments in Cambridge, and Mayor Bellucci said, no.
He didn't want it here.
Nope. You can't do recombinant DNA in Cambridge until the city of Cambridge tells you you can. And there was hearings in City Hall. And then a really interesting procedure where citizens from Cambridge were volunteered for a committee. They met with scientists, learned about the technology, learned about the hope of the technology, and ultimately came about a year later to the city council and said, we think this should proceed. Mm-hmm. So because then the city council issued regulations for recombinant DNA labs. So when Biogen moved into Cambridge, they went to the city manager and said, we'll adhere to these guidelines. Will you approve us building a lab here? And they said yes. Mm-hmm. So you were the only city in the country who had city regulations for doing recombinant DNA.
And that became the moment.
That's why
I find it so ironic and lucky that this moment that was built to stop the biotech industry led to it really having a home in Cambridge because it was predictable.
Yeah, it was predictable. And you can't make an investment of, tens and more millions of dollars building a facility, renovating a facility, unless you know you can do something in it. So the regulations were really critical.
That's really fascinating to think about that history. So take us from that moment to today.
Well, there's more to this.
Yeah.
Regulations in the high-tech medical industry are very important. That's why the FDA is very important. If you have a set of rules, you can satisfy those rules and you can get approval. But if that's changing, mm-hmm. or if that's unpredictable, then the amount of investment you're going to get will go down. Because uncertainty is the most negative thing you can have.
Because there's enough risk in the science.
It's enough risk in the science. You don't want risk on the other end when you've got something that works.
That takes us to exactly where I wanted to take you, which is this moment in biotech where we have that uncertainty and a little bit of chaos that we're working through. At the same time, we have tools like we've never had before in science. What do you make of this moment?
I think the moment in somewhat is created by the uncertainty and chaos that you're talking about. And that's a pretty heavy blanket on the industry. The innovation side is really rich and is becoming more relevant, more impactful. We've made stunning advances in immunotherapy treatment of cancer. We're going to have more. We've got scientific advances in how we understand the nervous system, mental disease, chronic mental disease, and others. We'll be able to treat those. We'll have treatments for things we don't even, are considered untreatable now. But, the system has got to be in a way that they accept and support and approve it. And if you don't have that endpoint, you won't have the investors at the beginning. And so I think that's coming back. I think we're at the nadir of it all, and we're going to see more investment and more innovation. But the last 5 years have been very difficult.
Yeah, ups and downs in biotech. We saw the hype with COVID and then the punishment afterwards. When we spoke a week ago, we talked about the fantastic basic science that's happening and innovation leading to new drugs, but healthcare delivery and the access for patients is not really where it should be. And in this country, we are paying a large amount of healthcare cost for not the very best healthcare in the world.
I think we have the best healthcare if you get sick and you're getting treated. But even there, it's my impression that the degree of innovation we have in the discovery, new treatment, new biology side is not matched by the innovation in healthcare delivery. We're spending 18 to 19% of our GDP for healthcare. That isn't, I mean, that's the upper limit of probably what our economy can bear. So we need more innovation in healthcare delivery. And that comes all the way from how to communicate better to, citizens, potential patients, how to deliver healthcare with people contact in different ways. I think nurse practitioners, physician assistants are going to become more common, supported by information and then ultimately by internists. So, and then healthcare economy and education, how to support patients in different locations. So I think there's going to be a growing impact of AI in that area. That is an opportunity for innovation and for companies, as well as for the discovery side. So I think that's what the next 10 years is part of what the next 10 years is going to be about.
Yeah, we showed you our new AI biohub at Lab Central, where hopefully some of these new solutions will be birthed.
How many GPUs do you have?
We don't have them in-house, but we give them access. When we met last week, I was trying to enroll you on this mission of defending science against the public discussion that's criticizing science, and you had a different point of view.
Well, I don't think you can defend science. You have to be, to people who don't understand what we do, you have to meet them where they're at and teach them what you're doing and why you're doing it and how you're doing it and what the uncertainty is in that process. I went down to the National Academy and was part of a meeting at the National Academy about 6 months ago. And the head of the National Academy got up and said, in essence, we have the truth. We have the truth. I get up every day wondering what the truth is, because everything is related to everything. You close down in the pandemic, you reduce infection, but you keep kids out of school. All right? How do you balance that? What's truth? How do you value that, impact of lower education for a whole generation of students against, the increased spread you get if you don't lock things down? And that type of trade-off is common of everything we do. So when you get up and tell people, look them in the eye and say, I'm a scientist, I know the truth, they know you don't know, right? And you got to meet them and talk to them and convince them that given the trade-offs, given the probabilities as you see it, this is the best way to proceed. But don't step in front of them and tell them I have the truth, because that's not going to fly. And it's really, I do think it's fun to have a community that you're trying to work with and can help them and meet them. It's part of the job of being an educator and being part of a scientific community. And we do it well here in New England.
Right.
We have a lot of communication with people, not in the other parts, many parts of the country.
Talking about community is another topic that we wanted to take up. At Lab Central, we try to build community for our innovators. And in some of the materials that I watched in preparation to get to know you a little bit better, community is also important for you, scientific community, and how it has to work together to get to a product. It's not the single scientist in most cases. Talk to us what community means for you in science and in business.
Community is everything. And it's really the most pleasurable part of doing it, because you can bring people around you, work with them, business people, regulatory, marketing, manufacturing, everybody, and they're all necessary to accomplish what needs to be accomplished. And you have to treat all of them with respect, thank them for what they're doing, and work with them to make things happen. And that gives you an entree to a whole diverse set of people and their lives and what they're interested in. And it also enriches you, because as you learn more about what motivates them and how they work, you see places where you can become involved, come help them in different activities. So the ability to create a community is important. Now, one of the things that's happening now in this particular time and place is that we have begun to substitute Zoom for community. Mm-hmm. Now, that's an assumption that you can build the community that is as functional as people in a room working together by Zoom. Mm-hmm. And we'll see. Clearly, some things are easier, some things are better. You can engage people at a distance much more effective than traveling all the time. But I'm a little concerned that we are losing something out of our educational interactions, productivity, by not being together more and being eye to eye and learning about people and just trying to motivate each other.
One of the principles that we've built Lab Central on is exactly that community, and we say we want to reduce friction and maximize collisions for people. Yeah. Meaning we want to bring people together in our corridors, in our cafes, at events like this. Thank you all for showing up, and not just on the live stream. So important.
Yep. No, it is. And so when you, let's talk a little bit about Alnylam.
Yeah.
Okay, so Alnylam grew out of a scientific discovery by Andy Farr in 1998 and Craig Mello. Andy was my grad student at MIT, so we were friends. We've kept in contact.
And he wasn't even a biologist to begin with.
He was a mathematician, and he came to MIT when he was 19. He wasn't legal until he got his PhD. So but he is brilliant, he was brilliant, and he was a lot of fun to have around. And so they made this discovery, and I make my living taking phenomena and turning it into chemistry. And so and David Bartel and Tom Telscholl and Phil Zamar, we developed a biochemical system that demonstrated the chemical properties.
So we're talking about the late 1990s now.
Right, in 1999, we started. And in 2001, we knew that these small RNAs were being generated.
So for who knows RNAi, or who does not know RNAi? Okay. Honest show of hands. RNAi, gene silencing, of course, the principle that underlies Alnylam.
So the principle is simple. You have a gene, you make double-strand RNA from that gene, and if an organism is sensitive to RNAi, that double-strand RNA will silence the gene. Mm-hmm. It was discovered in nematodes. And so that was stunning. As soon as I read that paper, I said, if this works in mammalian cells, we have a whole new ballgame. It was the CRISPR of the day. It was just a stunning way of silencing a gene. So we worked out the biochemistry of it, and the group got together and said, if you can translate this to human disease, you have, the genome was just determined. We had the genome sequence. We knew a gene that caused disease.
Now we can silence it.
All we have to have is the sequence. And we can design an RNA, and then the big issue is, could we introduce the RNA into human cells? So that was the delivery problem. And so, two things. When we decided to do this, I came up to Millennium and asked Jeff Leiden if I could make a pitch to Millennium with the team. And we made a pitch. I knew they couldn't take it because they had other problems they had to deal with. But it was the most exciting company in Cambridge. Mm-hmm. And by talking there, everybody in Biotech learned that we were thinking about starting a company. And therefore, the venture capital came. And so we launched the company with Polaris, and Chris Westphal as the CEO. And we recruited the management team out of Millennium. Mm-hmm. So John Maganori came out of Millennium and became CEO. But 2002 was a difficult time to start a company. I mean, we were in one of these biotech lulls. Yeah. Not as bad as it is now, but it was really a very difficult time. And we got some relationships, and John Maganori was a wonderful, and is a wonderful entrepreneur. And so we were able to launch a company and solve the delivery problem with lipid nanoparticles, right, which became Moderna's method for delivering mRNA. Right. And it's going to become the method of delivering RNA vaccines to treat cancer. And it's going to become the method of RNA delivery to CAR T cells to enhance immunotherapy. So it really took science building on science. Mm-hmm.
And the whole community of scientists.
And the whole community. Yeah. Moderna spun out of that with Bob Langer and others as founders. And
And now Alnylam has multiple approved therapies on the basis of siRNA.
6 and more growing. Yeah.
I also enjoyed you telling the story of how you sent Tom Tuschl out to find that sequence or that structure that actually induces RNA interference.
Well, Tom Tuschl had come from Germany.
German guy.
Yeah, yeah. There's good science in Germany. And Tom came to do a postdoc with myself and David Bartel. And we had him working on splicing. And sorry to tell you, the folks, the project I gave him to do and he wanted to do, we should never have done. Because if we really thought through to the other end, we'd know there was not an answer there. But he worked on it. We published a paper. It was interesting. But he had 2 months left before he had to go back to Germany. And he said, well, do you want me, he came in to talk about what he wanted to do. And do you want to continue or do you want, and I said, why don't you take these 2 months and try to see if you can get a biochemical reaction with RNAi. And he then went off and engaged Phil Zamore and David Bartel. And the first experiment Friday afternoon, he walks in my office and says, I think we have a signal in a biochemical reaction that shows specificity. And so I go home, and he works all weekend. And he carries out the titrations and everything, and he comes in next week. And he showed, this 20-fold signal that said this is happening in a biochemical reaction where we can really make it happen. And then we had to solve the delivery problem, and that was lipid nanoparticles and TTR as a disease target in the liver. And then we solved the delivery problem another way, and that was sub-Q, not IV. And now, the secret of Alnylam.
Now it's an accepted modality.
It's an accepted modality. Yeah. I mean, there are probably 10 RNAi firms out there. And whether it'll work in the central nervous system is the big frontier. There's some evidence that suggests it will. And if you can get gene-specific inhibition in the central nervous system, I think you can do some wonderful things. So it's science. We couldn't have done this 10 years earlier because we wouldn't have had the human genome. If you have the human genome, then you can do this sort of thing. If you have lipid nanoparticles, you can do, RNA vaccines. If you have RNA vaccines, you can do CAR T-cell delivery. It's just, it grows on itself. It's one of the more exciting ways you can have your day-to-day existence.
I think that's so interesting because you span multiple decades now of science and also the business of science. Yeah. And you have this perspective of founding Biogen in the 70s and then Alnylam in the 2000s, and now we are 20, 25 years later, and to see what's different and what still remains the same between those periods.
Well, what's different is the science is much more sophisticated, and it's going to be mixed with AI, which is really dependent on large amounts of data, which we will get, which will allow us to formulate our hypothesis much more precisely and identify the causes of genes much more precisely, and then be a higher probability that when we make our investments, we will be able to be successful. And even in the process of designing chemicals, drugs, we will be using AI. In the process of understanding systems, physiological systems, we will be using AI and big data. In the process of guiding patients to the right place, the right physician, the right treatment, we'll be using AI. To the process of calling them in the morning and asking them if they took their meds,
right.
We'll be using AI. So
So you're not scared of the AI wave that's crashing down on us?
It's almost the same as recombinant DNA. I mean, there's things that are going to be displacements.
Yeah.
One we're talking about is, the impact on social media and how that's going to influence things, and that's very important. And then the other thing we're going to need to think about is economic displacement, because there's going to be a lot of jobs that are not as difficult. Fewer people can do more. And then what's society going to look like? Because the ability to work, the opportunity to work, to be meaningful in what you're doing is very important in people. And, it'll be interesting to see what the next 20 years holds, because a lot of us are going to be doing things that are different than we are now.
Thank you so much. We will want to look in the future. There's one question that an audience member asked me to put to you that I do want to put in before we open it all up for all of you, which was, he wondered if you won the Nobel Prize, and that's sort of the highlight of a scientific career. and many scientists aspire to even a tenth of that attention. But he was asking, is there anything non-desirable about winning the Nobel Prize?
Well, there's lots of things desirable.
Yes.
And one of the most pleasant parts of winning a Nobel Prize is to go to Sweden for a week to celebrate it. I have never experienced anything as uplifting and wonderful as that week. They give you an attaché, they give you a car, they take you to the best restaurants, you talk to them, you have the best musicians, opera singers, dinners, goes on for a week. You have an intimate dinner in the City Hall for 1,100 people with the king and queen. All right? And then you go to the opera house to get your award, and everybody applauds. And then you go to that dinner, and then you go to a nightcap where they try to get you drunk. and my middle daughter at that stage was in college. She was a sophomore. She got up. We went to the cocktail party, not cocktail, nightcap. We went home at 2, Anna and I. She went home at 4.
Oh.
She went back to the hotel, changed her clothes, walked out the door, got in a cab, went to the airport, flew to Philadelphia, went in the next morning and took her final in biology.
Wow.
Now, she got an A in the course, but I don't believe that final was that good. So I think the A in the course came from the notoriety of what she was doing.
That was helping.
But that was really, I mean, and then you're on a list all through the country. So anyone organizing a meeting, you have 20 people on the list. Who are you going to invite out of that 20? Well, that fellow or person just got a Nobel Prize. Why don't we invite them? So you're on that. And then, I mean, there's a downside to public exposure. And in my case, it was a Unabomber. And the FBI called us at 2 in the morning and said, we have a reason to think that you might be targeted by the Unabomber. Now, the Unabomber had bombs that explode out of packages, had damaged 23 people and killed 10 of them. And they said, don't open your mail. And then I said, I don't open my mail. My assistant opens my mail at MIT in the morning. Somebody has to be there before she could possibly open the mail. So for the next month, the FBI scanned my mail at MIT and in Newton. They intercepted a letter, but not a bomb. And but I continued to do my work and travel. I got security everywhere I went. But there's always a other side to things. But I will make a recommendation. If somebody calls you at 6 in the morning and says, will you accept the Nobel Prize, which they ask you, I would say yes.
That's a great moment, I think, for us to turn it over to the audience. We have a few minutes to take direct audience questions for Dr. Sharp. Please, if you have some, we have a microphone over there, and so you can ask your direct question of him. Daniele, right here.
Thanks so much. Looking back over your life and your career, what's the thing you're proudest the most?
Oh, what's the thing I am most proud about? I'm proud of, I'll phrase it this way. If on that list is the discovery of RNA splicing and the recognition of a Nobel Prize and being a leader in science. On that list is starting Biogen and helping to cure multiple sclerosis, TTR, a host of diseases that control people's lives, right? If I had to give up one of those, I'd give up the prize if I could do the other. But, they're both on that list, and they're wonderful. But if I have to give up one, in some theoretical life in the future, I'd rather help others directly by creating new medicines, new treatments, just doing science and helping other people.
Hi, thank you very much. It was very inspiring to listen to you. My question pertains to one of your comments about AI. I think there's a lot of companies that emerged over the last decade that use machine learning and AI in very creative ways, like Tempus, like artificial cell staining. Is there an area in biotech or in healthcare where you think that the impact of AI is exaggerated or doesn't have the potential that people think it has?
It's all exaggerated. And it's almost identical in what happened in recombinant DNA. So we had a discovery. It was on the front page of the New York Times. It was going to create a whole new industry. And then people started thinking about it and said, oh, you could create, disease here. We don't know what's going to happen. We don't know what economic impact it's going to be. And then there was a great deal of debate. That's why we had this debate in Cambridge. That's why there was a national debate. And then the next step in it, you start, and then everybody says, well, where's all these benefits? You promised me on the front page of every newspaper that there would be benefits from this. Where are the benefits? And you're losing money? Not a little money, you're losing hundreds of millions of dollars of money. Where's the benefits? And then they start emerging. At the same time, there's debate about the risk and everything else. So it'll play out in that form. But I think it will have ultimately, 10, 20 years from now, a bigger impact than most things we're debating right now. That's the way I see it. It's not going to be the single technical advance. Computing with quantum computing, which we will get, next 10 years, we'll be able to carry 100 times more computing capacity on our cell phone than we can now, with a lot more memory, coming instantly. Algorithms that will solve problems when you phrase them correct and give you suggestions for what you can do. And media you can't even imagine. So it's a big change, and it's going to ultimately change everyone. Medicine, there's a targeted population. This is everybody walking on Earth. So it's really an exciting moment. I can't anticipate how it's going to work out, but boy, I'd sure like to be here. Probably not going to happen, but I'd sure like to be here. I think it's terribly exciting. We've not, in the history of mankind, seen anything like it.
Cameron.
So with those exciting words about the future, what one or two pieces of advice would you have for young scientists who are going to make all these changes happen over the next 20 to 30 years?
My only advice is be optimistic, take risk, because you almost have to take risks. You have to ask, you have to pursue, or you never get the word yes, all right? And the support you need. And don't get discouraged. It's really, it's easy to get discouraged and turn away. But if you have people around you who are, supportive and help you and contribute with you, make a community, and I think the opportunities are wonderful. But it's a time, we're in the middle of a mood of uncertainty and pessimism in some way. And I think it'll turn and we'll be much more optimistic, but it's a complicated time. Don't get discouraged. There is an opportunity there. You just have to find it and get to it.
Oh, right here.
Thank you so much for being here. And thank you for your contributions to RNA and mRNA. And in recognizing that, I'm just curious, it's kind of maybe a funny question, maybe not. But with your contributions to RNA and mRNA, did you know Bob Langer at the time? Did he invite you to join in on Moderna? And if not, do you give him a hard time about it now?
Oh, yes, I've known Bob since I came to MIT 50 years ago. We've collaborated. We have a joint postdoc now. When we started at Alnylam, we invited Bob to be on the scientific advisory board, and he actually made major contributions with Dan Anderson at MIT to the whole lipid nanoparticle. I mean, we took the concept of lipid nanoparticle that Peter Cullis really contributed a lot to, and increased the efficiency 1,000-fold, and introduced the type of chemistry where the lipids actually are metabolized after they are introduced into the body to make that technology something that could be used. And then Bob and others started Alnylam with messenger RNA, and we talk. But I had Alnylam at that stage, and he launched Moderna, and that's fine. I had.
Thank you very much.
Thank you.
I got him in my arm.
Yeah.
Here's another.
You can be, you have to have a focus. Yeah. You have to have a team that's got enough time to really put your effort to it. And the folks who put Moderna together saved our you-know-what.
Thanks for sharing this time with us. It's been great to listen. I think all of us are going to go home for the holidays and spend some great time with family soon. What are you excited about coming back to immediately? Like, what are you working on right now that has you excited?
Oh, I'm excited. I'm working. My last investigator in my lab is going to leave at the end of the year. And he's got a great job down at Columbia, and he's going to be supported by Chan Zuckerberg. He's in a sweet spot, Jay Mahat. But I am on the scientific advisory board of DuPont, which is trying to take the new science of condensates and turn it into a process of developing drugs to treat untreatable disease. And Skyhawk, which is developing oral drugs to shift splicing and treat disease. And I'm optimistic that both of them have a real chance to make contributions. And then I'm on several boards, mostly nonprofit now, and chair a number of committees at MIT. MIT is a very dynamic place. You look at us decade by decade, we're different as a university in what we do. And so I enjoy being there and helping and working with others who try to make change. It's very important. But I don't have trouble getting up in the morning. Life is really quite exciting and lots to do.
Thank you so much. Really inspiring stories. I listened to a lot of the names that you talked about, some very famous scientists, people that we know here in the Boston area. But one surprising thing is I'm not sure I heard a woman's name in all of that list. I'm just wondering, how is that possible, and did CRISPR change that? And if CRISPR didn't change that, what do we need to do as female scientists to be part of these stories?
Oh, we're talking about events. I don't want to make excuses. All right. There are a large number of women scientists who are contributing enormously to what we're doing. If you watch the documentary Cracking the Code, which is the one Bill Haney has, Melissa Moore is featured there. She came from my lab. She went to Brandeis, then at University of Massachusetts, elected to the National Academy, Chief Scientific Officer at Moderna, and is mostly consulting now. Rachel Myers, trained in my lab, went to Millennium. We recruited her to Alnylam. She became Senior Vice President of Research and ran the research at Alnylam. Claire Moore, early professor, she's a professor at Tufts and had a wonderful career at Tufts. So I agree with you. There are not a lot of women's names in those early days. But I think, well, that is changing. There's no question about thinking about it. It's changing into the betterment. And I think I don't want to be naive. It's still more difficult. It's a more complicated world. But it's getting less difficult for women to have great careers. And I've always enjoyed working with my female colleagues. It's just a better environment when people are contributing from multiple backgrounds and multiple differences.
Thank you. I think this is a very important topic for us to consider and end on, Phil. From all of us here at the large Lab Central community, our deepest thanks for spending time with us here today and for all you do for science and for humanity, really. Very inspiring. I think we all leave with lots of thoughts and hope for the future. So that's really great.
Thank you. If you're interested, watch the documentary, Cracking the Code. It's available on PBS and Independent Lens. And I was told yesterday that 1 million households have now watched it.
Let's make that 2 by year's end. Let's make that 2 by year's end.
I would be delighted.
Yeah. And so thank you all for coming to join us for this live taping of The Dish. in the room and online. And thank you especially to the Lab Central team who made this huge production possible. I look forward to continuing the conversation with all of you about science in and around Kendall Square. And now we send you home to your families to continue the discussion about science over the holidays. Thank you very much.
Thank you.
Thank you so much, Phil. Thank you.